Good morning. So today I'd like to finish up our discussion of Chapter 5 and hence all the material, well, with the homework and everything that we'll be covering up through the midterm. So we're talking about paracyclic reactions now, right? Chapter 5 sort of got us a review of molecular orbitals and then got us into paracyclic reactions, and we started talking about electrocyclic rearrangements. There are two other main classes of paracyclic reactions, cycloadditions and sigmatropic rearrangements, and we're going to talk about those today. So remember, these are all reactions that don't involve intermediates, that involve reorganization of electrons and bonds in the formation of products. So when I introduced cycloaddition reactions, I gave us as sort of a classic example the Diels-Alder reaction, the reaction of an alkene with a diene with 6 electrons moving around in a ring to give a 6-membered ring to give a cyclohexene product. And I also cautioned you that although I've drawn this without any substituents, I've drawn this as ethylene and butadiene. Ethylene and butadiene would make a terrible Diels-Alder reaction. You typically need to have an electron withdrawing substituent on the alkene component, or conversely, you actually can go ahead and have electron withdrawing substituents on the diene and an electron donating substituent. That's called an inverse electron demand Diels-Alder reaction. All of these reactions involve orbitals, and all of them involve Humo-Lumo interactions, or perhaps to put it another way, all of the paracyclic reactions can be thought of as involving Humo-Lumo interactions, and all of paracyclic reactions involve transforming the orbitals in the reactants into the orbitals in the products by a smooth and continuous process. Now, the reason you need an electron withdrawing substituent for the Diels-Alder reaction is that it better matches up the energies of the orbitals, the HOMO of the diene with the LUMO of the dienophile. But that's getting a little beyond the scope of this course because we're really only talking right now about orbital symmetry and about what reactions can occur and what reactions can't occur. So Diels-Alder reaction, we call it a 4+2 cycloaddition. And that name is a little bit funny because you'd look at this and you'd say, well, obviously we've got 4 atoms here and 2 atoms here. You'd say it's 4+2, but this is really referring to the number of pi electrons. I'll say pi electrons involved. So for example, there's another class of reactions, and this is confusing as heck. There's another class of reactions called 1,3 dipolar cycloadditions with a 3-atom component, for example, a 3-carbon component or 3 heteroatom component. And people will say it's a 1,3 dipole because it has 3 atoms. Those 1,3 dipoles participate in 4+2 cycloadditions because they have 4 pi electrons that are involved in the process, or at least I should say more broadly, 4 electrons. Anyway, suffice it to say that the 4 refers to 4 electrons on this component. The 2 refers to 2 electrons in this component. And as I said, we are transforming the orbitals of the reactants into the orbitals of the product. And a shorthand that we can do to see if this transformation can occur and to see how the transformation occurs, specifically the stereochemical course, is to look at the HOMO of one component and the LUMO of the other component and see how you can get favorable overlap. See how you can get overlap of positive orbitals with positive orbitals, or positive orbital coefficients with positive orbital coefficients. That's what I draw as white. And negative orbital coefficients with negative orbital coefficients. That's what I draw as black when I show you my little linear combinations of atomic orbitals. So our butadiene component has 4 electrons, and remember when we started talking about the molecular orbitals of butadiene, we said that we can have 4 psi molecular orbitals, 4 pi-type molecular orbitals, in which we place the 4 pi electrons. So we go 1, 2, 3, 4. Psi 2 is the HOMO of butadiene. Psi 3 is the LUMO of butadiene. And then the other component is ethylene, or more specifically a dienophile analkene. And we have the pi, and I'm going to try to draw them at the same levels, sort of between the psi 1 and psi 2 for pi of ethylene, and between psi 3 and psi 4 for pi star of ethylene. And so again, we have a HOMO and the LUMO. And in the transformation of orbitals, then, we're going to be looking at the overlap of the HOMO of one component with the LUMO of the other component. It really doesn't matter which one we're looking at, because ultimately the HOMO and LUMO of the components are being transformed into new molecular orbitals. Every molecular orbital, in fact, in the components is being transformed to a molecular orbital in the product. So if I, for example, take the HOMO of butadiene, psi 2 of butadiene, right? Psi 2 of butadiene, the linear combination of atomic orbitals that we use when we make up psi 2 is we use the 4 p orbitals and we combine them in such a fashion that we have one node in the plane here, orthogonal to the olefin, orthogonal to the diene. So here's our psi 2. This is the linear combination of atomic orbitals. Remember then in the molecular orbital we sort of get a cloud over here, a cloud over here, a cloud over here, a cloud over here, but no electron density. So we can use these orbital coefficients to help us see how we can combine our orbitals to form the new orbitals of the product. So here's our HOMO of the butadiene. We'll look at the LUMO of the dienophile, the LUMO of ethylene. That's just a pi orbital. And we will see, whoops, the LUMO, not the HOMO, the LUMO of ethylene. And you'll see that we can combine the HOMO and the LUMO, and we get a net overlap at both points. In other words, we're set up to form the new sigma bonds that we get in the product. So in other words, the diene swoops in over the dienophile, and we are forming the new bonds. We're set up to get those new bonds here.
Can you not do it the other way around?
Absolutely. The question was, can you not do it the other way around? And for the purposes of this course, there's really no difference. In practice, if you have an energy difference, if you, for example, put an electron withdrawing substituent over on the dienophile component, that's going to bring down the energy of the LUMO. That's going to make a more significant orbital overlap with the HOMO. But in practice, you can look at either combination. So we could just as well go ahead and look at psi3. Psi3 is the LUMO of the diene. The linear combination of atomic orbitals that make up psi3 is like so. We now get 2 nodes. And so we can do that same drawing over here. And so now we get our LUMO. And now we get our pi orbital of the ethylene, the HOMO. And so in both cases, we get favorable overlap. I'll say overlap leads to bond formation, or more specifically, the fact that we can get this favorable overlap, white with white, black with black, means that we are set up to mix those orbitals in the transition state and start to form the new bonds. Thoughts or questions? Yeah.
Is there like one that's preferred to either do like the LUMO of the diene?
Is there one that's preferred? As I said, typically when we have an electron withdrawing group, which would be your sort of normal Diels-Alder reaction, where you would typically have an electron withdrawing group on the diene and maybe an alkyl group or a methoxy group on the dienophile, that raises the orbital energy levels of the dienophile, and that the electron withdrawing group lowers the orbital energies of the diene. So yeah, technically in most cases, the HOMO of the diene with the LUMO of the dienophile would be a more important interaction. But for looking at what's allowed, you don't need to worry about this. Yeah.
And the reason for that is because what we're like semi-ignoring is that the only way the orbitals can mix is they're of similar energies.
The only way the orbitals, in practice, you're right, the only way the orbitals can mix is if they're of similar energies. And this is one of the reasons why the Diels-Alder reaction, as I've written it, with butadiene and ethylene is such a bad reaction, in practice, one that wouldn't typically occur.
Can you just tell from which face the diene is attacked?
So face. Now we start to get to great questions. So we've got 2 issues of face we're going to see. So one issue, when we started to learn about stereochemistry, we learned that in many cases, unless you have a plane of symmetry, you have a ray face and a C face. And this is an intense area of interest in controlling stereochemical course of reactions, because that will set a new stereocenter when you form sp3 hybridization, or it can at least. This case, you don't generate a chiral center. And so the answer is absolutely yes, and people have developed very clever strategies where they go ahead and first you have chirality in the system. Often you will have a chiral substituent, what's called an auxiliary, built into one of the 2 components. Kind of like we talked about, remember I talked about the aldol reaction. We only went so far as to say the E prefers prefers anti, the Z enolate prefers syn. The E enolate prefers anti, the Z prefers syn. In the absence of chirality, you will get both anti-diastereomers or both syn diastereomers, both anti and enantiomers or syn and enantiomers in equal amounts. But once you start to throw chirality in there, for example, a chiral group called a chiral auxiliary in the aldol reaction, then you prefer one enantiomer of the 2 syn or anti-diastereomers. Similarly here, once you start to throw chirality in, you can, and indeed there's a whole area of organic synthesis that focuses on development of chiral auxiliaries and chiral catalysts to facilitate that reaction. So absolutely. great question. But we're going to speak right now about a more pedestrian but nevertheless equally profound aspect of stereochemical control, which is the relative stereochemistry internally. And so in the Diels-Alder reaction, potentially we are generating up to 4 stereocenters. So let me give us an example. Let us take EE24-hexadiene, and let us take fumaric acid. That's the common name of this dicarboxylic acid. So this is a Diels-Alder reaction that really would occur, could occur, in the sense that you've got now an electron withdrawing group, 2 electron withdrawing groups, in fact, on the dienophile. And what's fascinating about this, so we do generate new stereocenters, and I want to show you something that is inherent to the Diels-Alder reaction and very cool and important stereospecificity. The Diels-Alder reaction has layers of stereochemistry in it. Everyone remembers, I hope, from sophomore organic chemistry that it is endostereoselective. That's a preference due to secondary orbital overlap. But the reaction is absolutely stereospecific in that the 2 substituents that are trans over here, basically the 2 substituents that are on, shall we say, the same side of the diene end up on the same side of the product. In other words, these 2 methyl groups end up on the same side of the ring. The 2 hydrogens, which I haven't drawn here and here, end up on the same side of the ring. Your 2 trans substituents on your alkene end up trans. And this is really important because this is stereospecific. In other words, you will end up with no product in which the methyl group on one position is trans to the methyl group on the other position. Obviously, if I started with a methyl group in this position, then you'd end up with only that. So if I started with the EZ diene, you'd end up with only a trans product. And here, you will end up with no product in which the 2 carboxylic acid groups are cis to each other. And this comes directly from the fact that in the transition state, as we are forming the bonds, so here's our methyl group, here's our methyl group, here's our carboxyl group, here's our carboxyl group. As we are forming these bonds now, we are forming them at the same time and locking in that stereochemistry. And this particular mode of addition that I've talked about as 4 plus 2, we can now be more specific to say that it is a pi 4s plus pi 2s cycloaddition. And the pi, of course, means that we are using pi electrons. You can also have cycloadditions that use sigma electrons. You can have, for example, sigma bonds doing the same thing in a cycloaddition. The S means suprafacial. Suprafacial means on the same side of the face. And so we are having this on the same face of the diene. In other words, we're reacting with this side and this side, not with this side and this side. This we would call anterofacial. Anterofacial is the opposite of suprafacial. And we are suprafacial with respect to the dienophile. We're swooping in above using the 2 lobes on one side not one lobe on one side and one lobe on the other side. That would be anterofacial. Yeah.
So this anterofacial has to do with like it bonding or like anti-bonding wise?
Not anti-bonding, but opposite side geometry. And that's what I'm going to show you next. All right. So let us take a look now at a 2+2 cycloaddition. So, let's take again in this minimalist style that I wrote a minimalist Diels-Alder reaction, let's take a minimalist view of ethylene plus ethylene, of course being some alkene, plus some alkene goes to a cyclobutane. So we have an immediate problem in orbital overlap. If I go ahead and look at a HOMO of one and a LUMO of another, so I'll just take a pi HOMO of one alkene and a pi star LUMO of the other. It doesn't really matter for the purposes of this discussion which ones I use. And you look at overlap, you'd say, well, we can overlap those two lobes. We can overlap those two components of the molecular orbital that match in sign, but we can't overlap over here, whereas in the other example, we were able to get overlap concurrently at both ends. What this is saying is that a pi 2s plus pi 2s cycloaddition is not allowed. It's forbidden. And I'll add just parenthetically thermal. Don't worry about that yet, because you're going to see, I'll show you the exception in a moment on this reaction. All right, this does not mean that cycloaddition reactions between alkenes do not or cannot occur. It means they cannot occur in a suprafacial fashion where both components are suprafacial, where the two components swoop in on each other. And yet there are other geometries, specifically an anterofacial geometry. Let me take a look at a real example which, alas, leaves no stereochemical signature. So the example here I'll give you is cyclopentene plus dichloroketene. Dichloroketene is a cumulated system. Cumulated systems mean you have two double bonds attached to the same carbon. Simplest cumulated system that you can think of, you are literally exhaling right now. And that is? Carbon dioxide, right? So dichloroketene is isoelectronic with carbon dioxide. So carbon dioxide is a cumulated system. Dichloroketene and many cumulated systems are extra specially reactive, both ketenes, which have an oxygen, and allenes, which have another carbon. And if I form dichloroketene, you can't put it in a bottle. It's not stable enough to isolate and put on the shelf. But if I generate it in situ, in the presence of cyclopentene, then I get the 2 + 2 cycloaddition product. And the way this cycloaddition occurs, bless you, is in a pi 2s plus pi 2a fashion. In other words, now, and I'll try to draw the orbitals as best as possible, now we have one of our orbitals. I'll draw it as the pi. Again, I could swap things. I could draw pi star, but I'll draw pi with pi star. I could draw pi star with pi. And what I'm going to try to do, and I'm not too good at generating perspective here, is I'm going to try to draw this other alkene component coming out of the board best as I can. So basically, this is my poor representation of the alkene on its side and coming out of the board. And now we're going to draw pi star, like so. And if you do this and you combine an overlap here and an overlap here, that is an antarafacial interaction. In other words, we are suprafacial with respect to one component and antarafacial with respect to the other component. And you can imagine that a ketene with its oxygen would be particularly good in taking the antarafacial role. So here's our cyclopentene ring, and here's the ketene. And the oxygen, if I just stick it under here so I get the pi bond of the ketene, is my arm here, the top of my hand. The oxygen's the tip of my finger. That oxygen doesn't have substituents on it to bang into the ring, so that makes it particularly good. Plus, as I said, ketenes are particularly reactive. So, in other words, this type of pi 2s plus pi 2a cycloaddition can occur. And indeed, although you can't see a stereochemical signature here, there are stereochemical consequences for the reaction. Substituents that started cis on this component would end up trans, and that is the key thing. All right. We talked before about photochemistry, and I said all of the rules in photochemistry swap because you promote an electron from the HOMO to the LUMO, effectively making a new HOMO. And as I said, all of this is a little bit of a simplification because we're really transforming orbitals in the reactant to orbitals in the product. But suffice it to say that in a photochemical 2 + 2 cycloaddition, then we have pi 2s plus pi 2s is allowed. In other words, everything that I said couldn't occur here now can. Like a Diels-Alder reaction, cis components in the reactants can end up cis in the product. And the way we can think of it, as I said, it's a little bit of a shorthand. But if here's our ground state, where we have electrons on the pi and electrons and a vacant pi star, in other words, our pi is our HOMO, our pi star is a LUMO, and we shine light of appropriate wavelength to be absorbed for simple alkene like ethylene, it would be vacuum UV, it would be below 200 nanometers. You will excite an electron from pi to pi star, and effectively now the pi star sort of becomes the HOMO in the reaction. And so now when you're dealing with overlap, you can think about overlap of your pi star excited state and your pi star of your ground state. So your pi star excited state, I'll say HOMO, and your pi ground state, or your pi star rather, ground state, HOMO. And there are some stereochemical consequences of this. For example, if I start with cis-2-butene and photolyze with vacuum UV, I'll say far UV is what you would call it, then the products that form are all cis coming together from basically one component swooping over the other with the methyls overlapped, and cis and trans. So basically you've got one component here, your stereochemistry is retained. You've got one component here, your stereochemistry is retained. These are what you would call superfacial products with respect to each component. But you don't form this product here, which would be superfacial with respect to one, but interfacial. So I'll say not formed. Yeah.
Sorry, I'm a little confused. So out of the two reactants, we are only exciting one.
Exactly, yeah. So basically, when you shine light on anything, a small fraction of the molecules at any given moment go into the excited state. When you wear suntan lotion, the light is, UV light is exciting the molecules and being absorbed. At any given moment, most of the molecules are in the ground state. For that matter, your blue shirt is blue because it is absorbing light. It is absorbing part of the visible spectrum. And in the same way, molecules are getting excited, but only a few at any moment, of only a small fraction at any moment. So there's lots of ground state butene, a little bit of excited state butene, and it reacts with the ground state butene.
So how do you have a HOMO for the pi star?
How is it a HOMO?
For the ground state HOMO. How do you have a ground state HOMO at an anti-bonding molecular orbital? For the one on the bottom?
Thank you. No, that's the ground state LUMO. Thank you. Other thoughts and questions? All right, well, as I said when we were talking about electrocyclic reactions, my personal preference is just to think things through and not remember rules. And in part because when you know one, you really know all four possibilities. But let me write out the four possibilities here so you at least have it for your notes. So, okay, so if we're looking at, I'll say, rules for cycloadditions, I could say that basically 4n electrons in the ground state has to be superfacial plus interfacial. For n plus 2 electrons, in other words, like the Diels-Alder reaction, in the ground state has to be superfacial plus superfacial 4n electrons in the excited state, meaning a photoreaction, is superfacial plus superfacial. And 4n plus 2 electrons in the excited state would be superfacial plus interfacial. And honestly, I think it is harder to go ahead and memorize this little table than it is to just go ahead and start with the HOMO and LUMO in whatever reaction you're looking at and think your way through. Thoughts or questions? All right, let's take a moment to talk about sigmatropic rearrangements. And I gave you sort of an archetypal rearrangement, the Cope rearrangement. We've also talked about various Claisen rearrangements in the homework, I think, at least the previous homework. So, okay, so if a sigmatropic rearrangement is a paracyclic reaction where you can think of a sigma bond as skating across a pi system. So let me just write a simple example, basically what I wrote before when I overviewed sigmatropic rearrangements, and I've just put on a couple of R groups here. So in the 3,3 sigmatropic rearrangement, in the Cope rearrangement here, and this occurs upon heating, usually to a couple of 100 degrees. In the 3,3 sigmatropic rearrangement, we've moved this sigma bond from here to here. And the term 3,3 sigmatropic rearrangement or the order, as we call it, the order of the sigmatropic rearrangement comes from the number of atoms you skate over. So over here, we go across 3 atoms, 1, 2, 3, 1, 2, 3, and we move our sigma bond from here to here. It doesn't matter which way I number it. But the point is we cross 3 atoms. The Cope rearrangement, the 3,3 sigmatropic rearrangements involving all carbon or involving carbon and 1 oxygen called the Claisen rearrangement. These are very common run-of-the-mill sigmatropic rearrangements. Here's another common run-of-the-mill sigmatropic rearrangement, and I'll draw the curved arrows and the new bonds that form. And we would call this a 1,5 sigmatropic rearrangement. And again, we can number across the system 1, 2, 3, 4, 5. The hydrogen gets number 1. And basically, if you look at this, the sigma bond on this side skates over 1, 2, 3, 4, 5 atoms. to arrive over here. And on the other side, the sigma bond just skates over the one hydrogen. So that's why we call it a 1,5 sigmatropic rearrangement. Thoughts? All right, let's look at the orbital symmetry interactions. We can think of this again in terms of Humo-Lumo interactions. And a good way to conceive of this is you can think of this sort of as occurring through a pentadienyl anion and a proton. That's a simple way to think about this. In other words, you can say up, we're basically having a proton here, and that allyl system, that rather pentadienyl system, has 6 electrons. The proton has 0 electrons, and they're combining them together. In other words, we can think of this as, and again, I'm going to draw this out once again. You can think of this as a pentadienyl anion. And H plus. So if we conceive of this in this way, you can say, well, okay, the H plus now has a vacant 1s orbital. So in other words, you can think of this as a 1s LUMO. And you can think of the psi3 of the pentadienyl system as the HOMO. So in other words, in our pentadienyl system, we have psi1, psi2, psi3, psi4, psi5. We populate our orbitals with 6 electrons. So this is the pentadienyl anion system. The psi molecular orbitals are formed by the linear combination of the p orbitals. Specifically, I guess we've been calling them the pz or 2pz orbitals from the 5 carbons. We can combine those 5 2pz orbitals in 5 different ways to make 5 molecular orbitals with increasing number of nodes. So psi1, we combine them all in the same phase and have no new nodes other than the node that's in the plane of the carbon atoms. Psi2, we get 1 node. So we combine our p orbitals like so to get 1 node. Psi3, we get 2 nodes. Psi3 is what we call a non-bonding orbital. There are no bonding interactions, but no direct anti-bonding interactions. Psi3 is non-bonding. It's at the 0 level. It's at the same level as 2pz. You go up 1 more level, you get 1 more node. You go up another level, you get two more nodes. But in psi2, you have 1 node orthogonal to the plane of the blackboard. In psi2, you get two nodes orthogonal. And so you look at this and you say, all right, what does this mean? And I'm going to try to draw the diene in perspective. and try to draw the linear combinations of atomic orbitals that make psi3. And here I'm going to draw my H1s. So this is our psi3 HOMO, and this is our H1s LUMO. Hydrogen doesn't have, or at least a proton doesn't have, an occupied molecular orbital. It has just a vacant orbital. And so if we look at the combination of the psi3, you find that this is then a suprafacial process with respect to the pentadienyl component. And there are direct stereochemical consequences. In other words, if I have a stereocenter on one end here, that stereocenter translates to a specific stereochemistry at the other end. And if I have a stereochemistry of a double bond at the right side of the molecule, that translates to a specific stereochemistry of the double bond at the other side of the molecule. And in practice, they go as pairs. If I start with one specific alkene stereochemistry and one specific sp3 stereochemistry, I get two products that have two paired stereochemistries. I don't get two other products. And this is a specific implication or a specific product of being suprafacial. To put this another way, chemists love to poke and prod at our understanding of structure and bonding. When organic chemists were working out whether these theoretical notions could be observed experimentally, people developed very clever experiments to poke and prod and say, okay, this is all really good in theory, but I can design an experiment using, in this case, isotopic labels and stereochemical labels to test it. And the reason we're talking about this now in 2016 is because in the 1960s and 1970s, people poked and prodded and said, oh my goodness, this is really true. And hence, this led to the 1981 Nobel Prize. So this is kind of cool and kind of important. In other words, stuff that you cannot see with your eyes can be observed with consequences that you can pick up with an NMR spectrometer or another instrumental technique to go ahead and say, oh my goodness, what we are only able to envision in our mind's eye really occurs. Let me give you one last closing example. The examples that we've just talked about are the most important examples. Let me give you a good counterexample and say, okay, let us consider a 1,3 sigmatropic rearrangement. In other words, let us consider whether this, and again, I'm writing this, I'll just write this with an R group over here. So this reaction, 1,3 sigmatropic rearrangement, is forbidden. And we're going to do the exact same conceptual exercise. We're going to consider this as an allyl anion. and a proton, just as we considered this as a pentadienyl anion and a proton. And we are going to look at Psi2 of the allyl anion, and we're going to look at the 1s of the proton. In other words, we're going to look at our HOMO and our LUMO. And again, we can make our pi-type molecular orbitals. Here's Psi1. We combine our p orbitals in linear combinations. Psi1 has no nodes. Psi2, other than the nodes from the p orbitals. Psi2 has one node. Psi3 has two nodes. And so we'll look at Psi2. And our hydrogen, and say, whoops, we can't get an overlap over here. In other words, specifically, suprafacial is forbidden. Suprafacial with respect to the allo component. And terafacial just say H1s, and terafacial is allowed, but geometrically it's impossible because you just can't span from all the way here to all the way here. So I'll say geometrically impossible. And the last thing I'll close with is in poking and prodding at these rules, which of course have been verified experimentally, people also found, I think this was Jerome Burson, demonstrated that if you have a migrating carbon atom, where now you're using a p orbital which has opposite signs, that opposite signs on the two ends, that works just fine, and you can migrate a carbon atom but not a proton across an allyl system in a 1,3 sigmatropic rearrangement. All right, well, that ends our discussion of Chapter 5. We'll get it in our discussion sections this week and in the homework, and we're going to pick up reading and talking about Chapter 6 on Wednesday.